Welcome to Hart und Trocken. In this video, I want to talk to you about sequences and their limits. Let us start with an example. A retired manager gets the following pension payment. The first part of the pension payment consists of a fixed payment of 30,000 euros per year. On top of this, he will receive additionally payments according to the following rule. In the first year, he will receive an additional amount of 25,000 euros, so that it will be 55,000 euros altogether in the first year. In the second year, he will only additionally receive half of this amount, that means 12,500 euros. So he will get 42,500 euros in the second year. In the third year, the extra amount of the second year is again divided by 2. That principle is continued in the fourth year. That means the extra amount in the fourth year will again be only the half of the extra amount of the third year, and so on. We want to find an explicit formula which gives us the total amount of money which the retired manager receives in the year number n. We call this total payment in the year n AN, which is a variable equipped with an index n. The basic payment per year is 30,000 euros. So we have AN equals 30,000 euros plus the extra amount, which start at 25,000 in the first year and is divided by 2 in each following year. We can express this mathematically by this formula. You see that in the first year, that means for n equals 1, the exponent turns 0. Which is why the expression of 1/2 to the power of n minus 1 takes on the value of 1. And we get the extra 25,000 euros. In the year 2, for n equals 2, the exponent takes on the value 1. And the expression 1/2 to the power of n minus 1 takes on the value 1/2. Which is why the extra amount, which is added in year 2, is only 12,500. It's obvious now that the extra amount is always divided by 2 for each increased n. A rule like this is called a sequence, which is short for sequence of numbers. This is the precise mathematical definition of a sequence. It is a mapping from the natural numbers n to the real numbers. To each natural number n, we assign a real number which we call an or f of n. Then we call the infinite list of numbers a1, a2, a3, and so on a sequence. An alternative way to write down the sequence is to put an into brackets followed by n element n. We can visualize a sequence just as we visualize functions using a graph. However, the graph of a sequence is a sequence of points rather than a continuous line. Let's have a look how the sequence of the total pension payments per year looks like. The sequence of yearly payments is given by these white points. So in the first year we get 55, well, this is in 1,000 euros. In the second year we get 42,500 and so on. The blue lines in between are just cosmetics. So what is striking here is that the white points approach a limit, which is 30,000 euros per year. The reason for this is obvious, because the extra amount gets multiplied by 1/2 from year to year, which is why it finally approaches 0. So in the later year, the payment basically only consists of the fixed payment of 30,000 euros per year. Mathematically, we say that this sequence approaches the limit of 30,000. Now let's have a look at the mathematically precise definition for a limit of a sequence. Admittedly, it's a little awkward to read and we have to get used to it. So let's read the text. If for a sequence an, a number g exists, such that for every interval around g, no matter how small the interval, almost all members of the sequence are within the interval, then we call g the limit of the sequence. By almost all members, we mean all members except finitely many. No matter how many these finitely many are, they might be billions. Compared to infinity, that's still almost nothing. If the number g is the limit of the sequence, we write lim n to infinity an equals g. There is an alternative, equivalent way of saying this. It is very condensed and we will go through it sign by sign. It is read in the following way. For all numbers epsilon greater than 0, no matter how small epsilon is, there exists a natural number n0, such that for all natural numbers which are greater than this n0, the distance between g, which is our limit, and the member of the sequence with a number n is smaller than this number epsilon, which we have chosen in the beginning. Now I suggest that you stop the video immediately, rewind, and listen to this definition a couple of times until you have really understood it. The following graphical illustration will also help you to understand it. The blue points in this graphic represent a sequence which is given if we assign to each natural number n the real number 1 over n. So the first values of the sequence are 1, 1/2, 1/3, 1/4, 1/5, 1/6, 1/7, and so on. Obviously, the sequence approaches the limit 0. However, this is only what the graphic suggests. If we want to go sure mathematically, we have to verify the definition which we have just discussed. In this case, the definition for the limit of a sequence translates to the following. For each interval around 0, no matter how small we choose this interval, there must be a specific position within the sequence, such that all following members of the sequence lie within this interval. That is the idea of almost all members of the sequence lie in the interval. Now do you see how strong this definition is? Because we say that this must be the case for any interval around 0, no matter how small we choose this interval. Let's illustrate this by specifying such an interval around 0. The borders of this interval are indicated by the two red lines. Then we see immediately that from the fourth member of the sequence on, all members of the sequence lie within the interval. So almost all members of the sequence, well, except for the first 3, lie within the interval. However, that is only a small part of the definition which we need to verify, because we said for all intervals, no matter how small we choose them. Now this is a much smaller interval, but the condition must also be fulfilled. That means, again, we have to find a specific member of the sequence such that all following members lie within the interval. Now we can have a look here by scrolling, and we see that around, let's say, the 13th member of the sequence, all following will lie inside of the interval. And we can continue this game, can make it even smaller. Well, that's too small. Let's say like this. And again, if we scroll, we will find some, well, that's hard now because it's very, very far on the right-hand side. Let's say around the 38th or let's say the 42nd member of the sequence, all following members of the sequence lie inside of the interval. Obviously, not every sequence has a limit. For instance, we can think of a sequence of numbers where the numbers get greater and greater in a way such that no limit is approached. For instance, just the natural numbers 1, 2, 3, 4, 5. That is a sequence which obviously doesn't have any limit. Now we'll have a look at a couple of examples and ask ourselves if they have a limit or not, and if yes, which value the limit has. We start with the limit we have just been graphically looking at. an equals 1 over n. We have already found that this sequence has a limit and that this limit is 0. So we can write limit n to infinity of an equals 0. The second example is an equals z with a constant z. This is simply a constant sequence where every member of the sequence has the same value. Obviously, this constant has a limit and the limit is z. Now this one is a nice one. It's an equals minus 1 to the power of n. Which values does this sequence have? Well, minus 1 to the power of n oscillates between minus 1 and 1. The sign depends on the question if n is uneven or even. For uneven n, we get minus 1. For even n, we get 1. Now does this sequence have a limit? Or does this sequence have even two limits, like 1 and minus 1? Let's examine the definition of a limit closely and have a look at the graphical representation. This is the sequence. As you can see, the blue points jump from -1 to 1 to -1 to 1 to -1 and so on. Now let's examine the question if, for instance, +1 is a limit of the sequence. To this end, we have to choose a small interval around 1, for instance this one. Now it's obvious that every second member of the sequence is contained in the interval. That means that infinitely many members of the sequence are contained in the interval. So is the condition in the definition for a limit satisfied or not? Well, it's not satisfied, because the condition says that for this choice of the interval, there must be one specific position in the sequence such that all following members of the sequence are contained in the interval. But as every second member of the sequence jumps out of the interval, there will never be such a position such that all upcoming members of the sequence are contained in the interval. And of course, this situation doesn't get any better if we make the interval smaller. It still stays the same problem. So we conclude that +1 cannot be a limit of the sequence. And, exactly following the same argumentation, we can also conclude that -1 isn't a limit of the sequence either. Altogether we find that this sequence doesn't have a limit. The last example we look at is 1/2 to the power of n. This sequence has the values 1/2, 1/4, 1/8, 1/16, 1/32, and so on. It is closely related to the first sequence we looked at, the yearly pension plan of the retired manager. It is obvious that these numbers approach 0 such that the limit of the sequence is 0. In fact, we can generalize this fourth example, because suppose we replace the 1/2 by any other number. Let's call this other number q element r. In which cases does the sequence still has 0 as a limit? Well, it's not hard to verify that this is the case exactly for all q element r whose absolute value is smaller than 1. If we take such a q with absolute value smaller than 1 and multiply it with itself for multiple times, we will discover that the result will get smaller and smaller, or more precisely, will approach 0. We can summarize this result in this way. For every q with absolute value of q strictly smaller than 1, we have that the limit of q to the power of n equals 0. Now let's do some definitions. If the sequence an has a finite limit g, finite means it's not minus or plus infinity, the sequence an is called convergent. So, a convergent sequence is a sequence which has a finite limit. Actually, according to our definition with intervals, limits are always finite, because it's quite hard to put an interval around plus or minus infinity. On the other hand, a sequence which doesn't tend to a finite limit g is called divergent. There are several possible behaviors for divergent sequences. For instance, they may tend to plus infinity or minus infinity. On the other hand, divergent sequence may oscillate between two values or between two areas of values, exactly like the sequence -1 to the power of n did in our example before. Now we often find ourselves in the situation that we want to calculate the limit of a given sequence. Sequences or formula for sequences are not always as simple as the ones we have been looking at. For instance, consider this sequence. If we want to find out if this sequence has a limit, and if yes, which value the limit has, it's good to have some rules how to deal with or how to find out limits of sequences which are the combination of multiple more simple sequences. In this case, the sequence an consists of these two more simple sequences. For both of these sequences, we already know that they have a limit and that the limit is 0 in both cases. By the way, using these arrows followed by the limit 0 and adding an additional n to infinity is a quick way to write down the limit of a sequence. Now if we call the first orange sequence bn and the second orange sequence cn, wouldn't it be nice to have a rule which allows us to calculate the limit of an of the sum of the limits of bn and cn? Because we know the limits of bn and cn, both are 0, the limit of an would also be 0. In fact, such a rule exists, and even more of them. Suppose we have two convergent sequences, an with limit a and bn with limit b. We then can use algebraic operators such as summation, multiplication, division, and so on in order to build new sequences from these two sequences an and bn. For these complex or combined new sequences, we have a couple of rules to find their limits. For instance, if we look at the new sequence an plus bn, or also an minus bn, we can calculate the limit of this new sequence as the summation, or respectively the difference, of the limits of an and bn. Also, we can build a new sequence from an by multiplying each member of an by a constant c. The limit of this sequence can be calculated as c times the limit of the sequence an. A more general version of this rule is if we build a new sequence an times bn. The limit of this sequence can be calculated as the multiplication of the respective limits of an and bn. So now the principle is getting clear. Whenever we build a new sequence using a mathematical operation, we can apply this mathematical operation to the respective limits of the original sequences to find the limit of the new sequence. A last version of this principle is given for the sequence an divided by bn. Here the same rule holds. We can divide the limit of the new sequence by dividing the limit of an by the limit of bn. As always, when doing divisions, we have to make sure that the denominator doesn't get 0. That means b and bn must not be equal to 0 for all n. We will use these rules for limits in an extensive way in a later video when we look at some examples of more complex sequences. Let us look at some more properties which sequences can have. A sequence an is called monotonically increasing if every sequence member is greater than or equal to its previous sequence member. And it's called strictly monotonically increasing if each sequence member is even strictly greater than its previous sequence member. Similarly, a sequence is called monotonically decreasing if every sequence member is smaller than or equal to its previous sequence member. And the sequence is called strictly monotonically decreasing if every sequence member is even strictly smaller than its previous sequence member. The sequence is called bounded from below if there is a constant cu, which we call the lower bound, such that all sequence members are greater than or equal to cu. Similarly, the sequence is called bounded from above if there is an upper bound. That means if there is a constant co, such that every sequence member an is smaller than or equal to co. And finally, a sequence is called bounded if there is a constant c such that the absolute value of all sequence members is smaller than or equal to c. Obviously, a sequence is bounded if and only if it is both bounded from below and from above. Now there is a close interplay of a sequence being bounded and a sequence being convergent. We have the following theorem. Every convergent sequence is bounded. So every sequence which has a limit is bounded. We can easily convince ourselves that this is true by looking at this example of a convergent sequence. As almost all sequence members lie within small intervals around the limit, there are only finitely many sequence members which do not lie within this interval. But they can be easily handled by choosing the bounding constant c that large, such that they lie all between -c and +c. In this case, we may choose c as 1.5. An alternative way of phrasing this theorem is, if a sequence is not bounded, it cannot be convergent. As I said, that is just an alternative way to phrase the first theorem. It follows from the first statement by propositional logic. Now look at this theorem. Every monotone and bounded sequence is convergent. Monotone means that it's either monotonically increasing or monotonically decreasing. To illustrate this, we look once more at our sequence an equals 1/n. Obviously, it is strictly monotonically decreasing and it is bounded from below. It is graphically obvious that the limit must be the highest lower bound possible. So if this red line indicates just any lower bound, we can try to increase this lower bound as much as possible. So finally 0 will be the limit because it is the highest lower bound possible, and because of the fact that the sequence is decreasing, it will be squeezed close to the limit. Of course, this is only heuristically speaking. To show that strictly, we would have to build a mathematical proof. For our purposes here, it is fine just to have an illustration of it without a rigid proof. So that's it for this video. In our next video, I want to demonstrate to you how to find the limits of sequences which are given by a more complex formula. Thanks for watching and see you next time.